Stars are born, live, and die through a process known as stellar evolution. This process is primarily driven by the interplay of gravity and thermonuclear fusion. The life cycle of a star depends on its initial mass. Stars with masses greater than about 8 times that of the Sun are destined to undergo stellar collapse, leading to the formation of a black hole. To understand stellar collapse and black hole formation, we must first explore how stars evolve and what happens when they exhaust their nuclear fuel. Stars form from giant clouds of gas and dust, called nebulae. Under the influence of gravity, these clouds contract, causing the material to heat up and form a protostar. As the temperature and pressure increase at the core of the protostar, nuclear fusion begins, marking the birth of a new star. The balance between the inward pull of gravity and the outward pressure from fusion energy determines the star's size, temperature, and luminosity. During the majority of a star's lifetime, it exists in a stable phase called the main sequence. Here, hydrogen atoms in the star's core fuse to form helium, releasing enormous amounts of energy in the process. This energy creates an outward pressure that counters the inward force of gravity, preventing the star from collapsing. The duration of a star's time on the main sequence depends on its mass. More massive stars burn their fuel more quickly and have shorter lifespans. As a star exhausts its hydrogen fuel, the core contracts while the outer layers expand, transforming the star into a red giant or a supergiant. In these later stages of life, helium and heavier elements are fused in the core, creating heavier elements such as carbon, oxygen, and even iron. As the star progresses through successive stages of fusion, the core becomes increasingly unstable. The key event that leads to stellar collapse is the exhaustion of nuclear fuel in the core. When a massive star reaches the end of its fusion process, it is left with an iron core. Iron fusion does not release energy, which means that without a source of fusion energy, the outward pressure supporting the star against gravity vanishes. This imbalance triggers a dramatic collapse. The collapse begins when gravity overcomes the pressure from fusion and the core contracts under its own weight. As the core collapses, it heats up, causing the outer layers of the star to be expelled in a violent explosion known as a supernova. The specific outcome of the collapse depends on the mass of the star's core. For stars with masses between 8 and 2025 solar masses, the core collapse results in the formation of a neutron star. For stars with masses greater than 25 solar masses, the collapse may result in the formation of a black hole. A supernova is one of the most energetic events in the universe. It occurs when a massive star's core collapses and the outer layers are expelled at high velocities. The explosion produces a shock wave that can outshine an entire galaxy for a brief period. The process leading to a black hole depends on the mass of the collapsing core. As the core of a massive star collapses, the gravitational pull increases, causing the core to become extremely dense. The outer layers of the star, no longer supported by fusion, are blown off in the supernova explosion. If the core's mass exceeds the Tolman-Oppenheimer-Volkoff limit, it continues to collapse despite the formation of neutrons, and a black hole forms. A black hole is formed when the collapsing core's density and gravitational pull become so intense that not even light can escape. This creates a singularity, a point of infinite density and zero volume, surrounded by an event horizon, beyond which no information can escape. The event horizon marks the boundary of the black hole, and it is the critical region where the escape velocity exceeds the speed of light. Black holes are regions of space-time where gravity is so strong that it warps the fabric of space and time itself. Understanding the physics of black holes requires exploring general relativity and the nature of space-time. According to Einstein's theory of general relativity, massive objects cause space-time to curve around them. This curvature is what we perceive as gravity. In the case of a black hole, the curvature is so extreme that it creates a singularity, where the laws of physics as we know them break down. The event horizon of a black hole is the boundary beyond which nothing, not even light, can escape the gravitational pull, This means that any matter or radiation that crosses this boundary is irretrievably lost to the black hole. The singularity at the center of a black hole is a point where the curvature of space-time becomes infinite, and the density of matter reaches an infinite value. This represents a breakdown in our understanding of physics, as no current theory can fully describe the singularity. An interesting consequence of general relativity near a black hole is time dilation. As an object approaches the event horizon, time appears to slow down relative to an observer far away. To an observer falling into the black hole, however, time would appear to pass normally, but from the perspective of an external observer, it would appear to freeze at the event horizon. For a star to collapse into a black hole, certain conditions must be met, particularly related to the mass of the collapsing core. The mass of the core determines whether the collapse results in a neutron star or a black hole. The Chandrasekhar limit, about 1.4 solar masses, defines the maximum mass of a white dwarf, the remnant of a low to medium mass star. If a white dwarf's mass exceeds this limit, it cannot support itself against gravitational collapse and will collapse into a neutron star or a black hole. The Tolman-Oppenheimer-Volkoff limit is the maximum mass for a neutron star, estimated to be about 2 to 3 solar masses. If the mass of the collapsing core exceeds this limit, no known force can stop the collapse, leading to the formation of a black hole. Black holes come in various sizes and are classified based on their mass. There are 3 main types: stellar black holes, which are formed from the collapse of massive stars, typically ranging from 3 to 10 solar masses; intermediate mass black holes, with masses between 100 and 1,000 solar masses, whose formation mechanisms are still not fully understood; and supermassive black holes, with masses ranging from millions to billions of solar masses, residing at the centers of most galaxies, including our Milky Way. They are believed to have formed early in the universe's history, possibly through the merging of smaller black holes or the accretion of massive amounts of matter. Black holes cannot be observed directly, as light cannot escape from them. However, their presence can be inferred through their interaction with surrounding matter. One of the main ways to detect a black hole is by observing its gravitational influence on nearby objects. For instance, stars orbiting a seemingly invisible object with a large mass can indicate the presence of a black hole. When matter falls into a black hole, it heats up and emits X-rays and other high-energy radiation. These emissions can be detected by space telescopes, providing indirect evidence of a black hole's existence. Stellar collapse and black hole formation are critical processes in the life cycle of massive stars. When a star's nuclear fuel is exhausted, gravity takes over, leading to a dramatic collapse that may result in a supernova and, in the case of very massive stars, the formation of a black hole. These fascinating objects continue to challenge our understanding of the universe, from the nature of space-time to the behavior of matter under extreme conditions. As our observational technology improves, we are likely to learn even more about these mysterious cosmic entities.